Hello and welcome to the talk. Today I talk about caterpillars hiding in tunnels or long paths in line arrangements. This is joint work with Hoffman, Parameterized, and I'm okay, so let me first introduce my co-authors. So this is Linda, she's currently at Technical University of Berlin. And this is Udo, who's currently in Brussels, and this is some drawing of the line arrangement. And we're in Berlin, so this is me and Udo. And let me tell you about what is a line arrangement. So this is a line arrangement, and it's a bunch of lines, and they induce some vertices whenever two lines cross, or a vertex, and edges. So any part of a line which is between two neighboring vertices is called an edge, and there's another edge, and then these bounded regions, they're called faces, maximum bounded regions. And they might be triangles, they might be quadrangles, and whenever two faces are separated by exactly one line, then they're adjacent. And what do I want to tell next?
So is the outer thing also a face?
Yes, this is an unbounded face.
Okay,
So, and what we want to find is we want to find the path in the dual graph. So this is a planar graph, and then there's a dual graph of it. And we want to find a path which is as long as possible, and so it visits as many places as possible. Okay, is the problem definition clear? Okay, so this is the aim of this book. So one thing you should remember is that the number of faces is roughly n squared divided by 2. As a rough estimate. We will also talk about alternating dual path. And here in alternating dual path, the underlying idea is that some of the lines are blue, some of the lines are red, and then this path alternatingly crosses red, blue, red, blue, red, blue. And you want to study how long these alternating paths can be. Obviously, there is an additional restriction, so we expect this path to be short. Okay, what has been done so far on this work? Basically, only one paper appeared there, and they had 4 results. So they showed that there always exists an alternating path of linear size. So this is just because they're between any two bichromatic faces. So a face is bichromatic if it's bounded by a red and a blue line, can be connected. There is a path between any two. And then there are just those two, there exist two bichromatic faces which are on the opposite side of the line arrangement. So in order to connect them, you need to cross a linear number of lines. So this is the first result they have. So, and they say their result is tight because if there's only one blue line, then okay, this one blue line has a linear number of edges, so every second edge must be blue, so okay, O of n is a true upper. This is clear? Okay. The next result is, so back to the monochromatic case, they showed that there always exists a path of length n squared divided by 4. So this is half of all the faces. So there always exists a path which covers half of all the faces. And as an upper bound, they gave an example where there is a path which, or there is a line arrangement where every path visits at most 2/3 of all the faces, namely n squared divided by 3. So questions to these results? Okay, this is basically the only prior work. And I want to show you this example. It's just, it's an example they didn't come up by themselves. It's just an example where we have a lot of hexagons which are white and triangles which are blue. So there are more of these white faces than of the black faces. So do you know that the graph induced the dual graph is bipartite? So the dual graph is bipartite. And then there are white and black faces, and here the white faces, there are just few of them, and that's why, because you alternatingly have to visit the white and the black face, at some point you run out of white faces. So this is very complex. So what did we do? As the first result, we made this upper bound tight. So they showed at most n squared over 3, and we show at least n squared over 3. So up to this little o of n term as this o of n term, this result is type null. This is our main result. And then we looked at alternating paths, and so we couldn't prove there too much, so we looked at random colorings. So you've given your line arrangement and you color randomly, what would you expect? And we could show that in this case you expect almost quadratic length of the path. So this is quite nice. And then we worked hard to make their counterexample more balanced. So they said, okay, what about one blue line? And here we show that if we give an example with 2 in red and 3 in blue lines, such that still the longest alternating path has linear length. So we would like to make it completely balanced. N red lines and blue lines, but we could not achieve this. And we also believe it's not possible. Questions for this? Okay, and for the rest of the talk I want to present you the key ideas of these three groups. Okay, yeah. First, why do we want to study this problem? First, it has a very natural formulation. It's as usual. Then there's this point line duality. So whenever you have a set of points, you can map them in a bijective way to a set of lines. And then many properties of this point set are hidden in this line arrangement. And then many algorithms which actually want to do something for points, they work on this line arrangement. Because there are many things that are more easily expressible. So hand sandwich cut is a very famous example, which basically only works in the line arrangement. So therefore line arrangements are kind of just as important as point sets, and point sets are kind of the most studied object in computational geometry. And then, what is the longest path is one of the most fundamental questions you could ask about line arrangements. Okay, so let's start with the monochromatic case. So here we want to show that we find a path of length n squared divided by 3, and you should remember these are 2/3 of all the phases, because n squared divided by 2 is the total number of phases. So how do we do this? So the idea is that we somehow define tunnels, which I will do in a minute, and then we find the path through the first tunnel, find an edge to the second tunnel, and then go through the second tunnel, and so on and so forth in an alternating way. This is a basic idea, and I will start with defining what are tunnels. So in order to define what are tunnels, I want to tell you what are levels. So the level of a line, so the level 0 of a line arrangement are all the parts of the line arrangement such that there's no line below. So for all this part, there's no line below, right? If I have this point and I shoot an array to minus infinity, then I will hit no other line. Consequently, level 1 is a part of the line arrangement such that there's exactly one line below. If I take any point here, shoot an array, it will hit level 0 at some point. And in the same manner, level 2, 3, 4, and 5 are defined. Is that definition clear? So, and so I colored now these levels, but okay, the line arrangement is monochromatic. And once we have this, these levels, we can define tunnels. So every phase between level 0 and level 2 is tunnel 1. Every phase between level 2 and level 4 corresponds to tunnel 2, and so on and so forth. And in this way, we have defined tunnels. And this is okay, and so the first thing we want to do is we want to draw this in a different way. So somehow this here is the lower bound of our first tunnel, and this is the upper boundary of our first tunnel. So we just want to draw this straight. And remember, so we have here this blue line, which is kind of alternating between the upper and lower bound. We can just draw it in a kind of arbitrary way. All we care for is that the graph as itself is the same. And this is just a very convenient way to draw it and to see more, because now things are much more visible than they're here. This is just a different way of drawing. This is clear? So you see, somehow there's a top, it has exactly the same face structure as here. And yeah, and then as I said already, then the idea is that we just go from the top tunnel and try to make a long pass from the most left to the right. We go to the next tunnel, and then we go from right to left, and to the next tunnel, and then and it's kind of clear that this works. And this gives already an bound of n squared divided by 4. So this very simple approach that I told you here, gives the same bound as these previous people had, and a much simpler way. So why is this? So you have to know something about line arrangements. So if you go very far to the left of your line arrangement and you number your lines 1, 2, 3, 4, 5, then the order very far to the right will be exactly the opposite. It will be 5, 4, 3, 2. Because here they're ordered by slope to the very left, and here they're ordered also by slope, but just in the inverse variant. Okay, so now let's say I have some tunnel and I have these lines above at the very left. Then they will be at the very right, they will be below. And the same, if these lines are above at the very right, then at the left they will also be below, just because of this ordering. So now, basically, if I know I'm in tunnel I know this, I have this many lines above on the left, this many lines above on the right, and all those lines I must cross. This means this gives me a lower bound on the length of the path for each tunnel. And I just add up for every tunnel how long this is. Like how many of these lines I will cross. That's it. And this gives us n squared over 4 minus O of n. Lower bound. Yes, as I said, the path must cross all of those. Any questions to this?
So you assume some general position of those lines?
Yes, I assume general position, otherwise the problem becomes trivial.
It's not true that in each tunnel you hit at least half of the faces?
It's probably true, but we want to hit 2/3 of the faces, right?
I mean, not for this lower bound. Not for this bound n squared over 4.
Could be true, but it could be, I mean, on average it's true. This is what we're saying, right? But it might be, for some of them, it might not be true for some tunnels. I don't know, could be, but I would not know. Okay, so we want to improve this. We want to get from n squared over 4 to n squared over 3, and this means that we have to traverse 2/3 of all the faces. This is the key. So, and in order to do this, we look at this tunnel, and so a path which goes from left to right will visit certain faces for sure, and will leave out the other faces definitely as well. And the faces which are left out, we call bad faces, and the faces which are traversed by the path, we call good faces. So what you can observe is that, so as we know, this is our tunnel, there will be a level which goes up and down in between. It might stay, but vertices are only on these tunnel boundaries. And there's exactly one line. So now what can this line do? It can go from top to bottom, right? So this would, and then the path must cross this, because this here separates the tunnel, right? So any face which has such an edge must be traversed, obviously. Now what could happen also that this middle level, it starts here, and the next vertex will be again here. Then obviously if the path goes in here, it cannot go out, because this has only one, we call it tunnel edge, and this is to one face. So if it goes in here, it should also go out here. So therefore we know exactly the faces which are traversed and the faces which are not traversed. And so to come to the title of the paper, those bad faces, they're they are the leaves or the legs of the caterpillar. So the whole tunnel forms a caterpillar, as can be easily observed. Yes. So what is the idea? The idea is that we try to incorporate these bed faces nevertheless. And the way we do this is we observe some additional structures. Okay, so what is this structure? So I will not tell you everything, but one thing that is very easily observable is if I have one bed face on the upper tunnel, then I cannot have a nested bed face on the lower tunnel. Can someone see why? Why is this impossible? There's some geometry involved here. So how many vertices has this face? It has 2, 1, 2. But we know in a line arrangement, every face has at least 3 vertices. Otherwise, I cannot, because I have straight lines, right? So I cannot have this cannot be realized with a line arrangement because, yeah, this has only 2 vertices. This is not true for unbounded face, but for bounded face, every bounded face has at least 3 vertices. So this cannot happen. And so, because this cannot happen, this means that every bed face has at most 2 bed neighbors, here and there. So this means max degree 2, this means all the bed faces are a forest of paths. So this is very nice. So all the bed faces are just paths. And this is what we will use. We want to incorporate these paths into into the normal path. Okay, so how to do this? So let's draw these paths here. So this path starts here, and then we have to prove that the first face connects to this path, to the original path, and well, the last face connects it. We don't necessarily need the last face, but we need some face to connect it. And it will turn out that if the path has an even length, we can incorporate all but the last face. So we would go step by step, but here we can do everything. So we have to prove that these 2 edges exist. And the same happens here. We have to prove that these 2 edges exist. And then we delete this part, and now we have normal path incorporating the bed faces. Okay. Yeah, I guess the reason why this edge exists is because this is the first vertex of the bed path. And the reason this edge exists is because, so there must be a good face above. And this good face must have a neighbor to at least one of those vertices from here. And we would just take the last one which we construct. Okay. So the question is this rerouting sufficient in order to show that we have traversed 2/3 of all the faces? And the answer is no, but imagine we would want to show now we traversed 2/3 of all the faces. Then there is a very simple argument you could imagine is you give every non-traversed face, so this face may be non-traversed, you give it a charge of 2, and this charge you distribute to 2 traversed faces. And we have there made up a simple rule. We just said, okay, one charge will be sent to the leftmost wall edge, and one charge will be discharged via the leftmost or the penultimate leftmost, or maybe the second vertex on the wall. So I guess it's easy to see on the picture, right? Okay. And then the argument is just, okay, so if now we have to show that every traverse face gets at most 1 charge, and no non-traversed face gets charged. So it could be that maybe this face charges now a different face which was not traversed, but this charge should go to traversed faces. Yeah, and well, actually, it can happen here after a careful case analysis that something gets double charged, and then we reroute again. But somehow, a little bit of magic happens, but we can show that the only way that a face gets double charged is if it's a good space, and if one charge comes from the bottom via an edge and one charge comes from the top via a vertex, or vice versa. And for this very specific, very structured situation, we can identify another set of edges which we can show are present, and then we can reroute again. Yeah, so it's a little bit magic. Why do these edges exist? And there are a lot of small observations which lead to it, but I guess I cannot show this here. Yes, but then we're done. We showed that to sort of all the faces are truths. And yeah, I left out some special cases, but I think these are the two or the three main ideas we had. Okay, questions to this?
So it left the first tunnel and then goes back to the first tunnel, or
so
here
yeah, it goes to the top tunnel, bottom tunnel backwards, bottom tunnel, or this is mid tunnel, then from the mid to the bottom and back here.
Okay.
So yeah. So actually this edge, which was traversed kind of in this direction, now gets traversed in that direction. Yeah, and to see that these edges exist, so this and this can only happen if it was the last phase of a bad path. So they must be farthest to the right. And then we use also that they have a degree constraint of 4. Okay, more questions to this? Okay, so this was our main result and the most technical part. So now I want to come to random coloring. So now we talk about alternating paths, which means that we alternatingly cross a red and a blue and red and blue and red. And here the result is that we suddenly go to almost quadratic. So somehow our paths become very long, despite the fact that this seems not to be true in general. For any line arrangement, just for random colorings. Okay, so how does it work? The idea is the same as before, but this time